All right, so you know, man, class recording has started. So, as we just finished discussing, right, if we can isolate the effect of gravity, we would see that all objects will accelerate at the same rate. Okay? Not that they feel the same force, they all feel different forces, but they all have different inertias as well. So the accelerations end up being the same. But that's, like you said, only under the influence of gravity. One thing that we have to contend with a lot here on Earth is air resistance, right? Our atmosphere, being a gas, right, has a low density, but it still exerts a force on things as you move through that low density gas. So, air resistance, right? A force of friction that exists when objects move through air. And we'll talk more about friction today. And the nature of friction. But it's a force of friction when it exists when objects move through the air. Something that's kind of, I don't know, weird or unique about air resistance being that, well, first, right, because it's a frictional force, it acts in the opposite direction and slows things down. But one of the things that is a little unique about air resistance is kind of an age-old question that sort of comes up when it's raining. Okay? So, I know, don't worry, I'll bring it together, right? So, it's raining and you have to make it from the car in the parking lot to the building that you're trying to go into. So you've got two choices, right? What are your two choices? If you don't have an umbrella, sorry. Okay, okay, you sprint or just walk, right? Okay, so let's go pluses and minuses, Nick. Nick, what's the pluses if you sprint? You get there faster, right? But what's the minus? You could trip and fall in the puddle. All right, I'll give you that, right? What's another minus if you run?
The rain won't affect you.
You might be running into rain that you otherwise wouldn't have run into if you were just walking, right? I mean, that rain that's up there, you wouldn't have hit if you were just walking, but now you're running, so you might get there, right? So, walking on the other hand, right? Yeah, you're going slower and you're in the rain longer, but you're not running into rain, right? Just the rain that hits you on the head. Kind of like air resistance in a way. What we find out is that as an object moves faster, the air resistance force increases. Because, just like when you run in the rain, you're running into more air per second, right? Air that you wouldn't have hit if you were moving slower or standing still, you now run into, right? This doesn't take into account things like running against the wind and stuff like that, but that would also increase your air resistance as well. If we're talking about still air here, okay? All right, so with that being the case, let's talk about the sheet that is attached to the back of that outline. So we'll come back and finish the outline in a second. But let's talk about this skydiver named Bronco. All right, so it says, Bronco skydives and parachutes from a stationary helicopter. Various stages of the fall are shown in the positions A through F. Using Newton's second law, right? And there's Newton's second law. A equals F net over M, okay? Let's forget about this part just for a second, right? This is Newton's second law. We'll come back to this, okay? Find Bronco's acceleration at each position, answering the blanks on the right. You need to know that Bronco's mass is 100 kilograms, so his weight is a constant 1,000 newtons. Air resistance, which is labeled as R, varies with speed and cross-sectional area as shown. Okay? All right, so first, let's talk about the weight, right? How did we get that his weight is a constant 1,000 newtons?
Multiply this mass by 10 meters per second.
Right.
Yeah, 10 meters per second squared.
M times G, right? That we know that the force of gravity is equal to M times G, right? And, right, mark here on Earth, G is equal to?
About 10.
About 10. And his mass being 100, right? So that's real nice and easy, make it 1,000. Sorry, Harris, 1,000 for today, just because, you know, we're going to make G10 for today. I apologize. All right, but let's start with these accelerations, okay? First, as soon as Bronco steps off of the edge of the helicopter in picture A, right? Is gravity acting on him? It's not a trick question. Sure, right? Gravity's always acting on him, even when he's in the helicopter, right? But at that moment, he hasn't started moving yet, right? This is that very instant when he steps off of the helicopter, steps off the deck of the helicopter, or whatever you want to call it. So because he isn't moving yet, his resistance is 0. Okay? What's the net force on Bronco in this position right here?
1,000.
1,000, right? Because we got one force, but not another force, right? Add them together, we get 1,000. Okay? What's Bronco's mass? 100 kilograms, right? So if we know his net force is 1,000 and we know his mass is 100, what's his acceleration going to be at that very moment? 10 meters per second squared, right? Because at that moment, what's the only thing affecting him? Gravity. And what kind of acceleration does gravity cause? How big of an acceleration does gravity cause? 10 meters per second. All right, so this is 10 meters per second squared. But as Bronco because gravity is accelerating him, what will Bronco start to do in this case? What type of acceleration will he experience in this case? Positive. Which of the 3 kinds of acceleration will happen here? He'll speed up, right, because of what's happening to him. So as he's speeding up, right, he's going faster. Except when we talk about air resistance, going faster means that you run into more air that you wouldn't have run into before. So now he experiences air resistance. And in the second picture, letter B, we see here that his weight is still listed as 1,000, but now he has a resistance force of 400. Does moving faster affect how much gravity is pulling on you? From this picture, what would you say? No. Gravity affects everything no matter how fast they're moving or which direction they're moving or whatever. That doesn't change. But the movement will affect the resistance force. Okay? So, in this case, in picture B, what is the net force that is acting on Bronco? Mark.
600.
600 newtons. Mark, which direction is the 600 newtons acting?
Down.
Downward. Now, in this case here, to kind of make things a little simple, right? Most people probably, if you had to pick, would call downward negative and upward positive. Kind of just makes a little sense based on math class and stuff like that. But here, because Bronco is moving downward and gravity is pulling him downward, they've decided to call down the positive direction. So this is positive 1,000, right? And that means that the resistance would have to have what sign?
Positive.
Which way is the resistance
Positive
going?
resistance.
Negative, right? So in this case, they've called downward positive and upward negative, right? When we take the net force, mathematically, what do we have to do? Technically, we do what? When we take the net force, technically we add. It's the sum of the forces, right? But when we add a positive and a negative, in effect, what are we doing? Subtracting. But really we're adding a negative number. So the net force here is 600 in the positive direction. That being the case, now we know the net force, right? Bronco's mass is still what? Did his mass change going faster? Nope. So that means his acceleration here would be what? In this case, 6 meters per second. Technically, Mark, what should we probably call it?
Positive.
Positive 6. Okay. This one here should be positive 10. All right. That being the case, now let's go to part C. Okay. If Bronco has an acceleration of positive 6 meters per second squared at picture B, what is he doing? Connor said slowing down. Sorry, Connor. Didn't mean to call you out on that, like on the video and everything. But if he's moving downward and he has a positive acceleration, what is he doing? He's accelerating. Which of the three accelerations is he doing? Positive, yes. Which of the three types of acceleration is still happening here? He's speeding up. Is he speeding up as much as he was before? Okay? His acceleration is decreasing, but his velocity is still increasing, right? He's speeding up, he's just not speeding up as much, okay? His acceleration has gone down from A to B, but what has happened to his velocity? It's gone up. He's going faster at B than he was at A, he's just not increasing speed at the same rate, okay? Now, C. What's the net force acting on Bronco at picture C?
0.
0, right? Andy, what would we say about Bronco at picture C?
He's not accelerating.
He's not accelerating, so we can make that jump right here, okay? 0 meters per second squared. How else could we describe Bronco at picture C?
Constant velocity.
Constant velocity. There's one other word I'm looking for. Equilibrium, okay? So Andy, let's go back to what you just said. Constant velocity, right? How fast is he moving at letter C? Fast or slow?
Fast.
He's moving fast, but he's not what?
Gaining speed.
Gaining speed, okay? When we reach this point right here, letter C, right? We refer to this as, let's flip back here. We refer to this as, sorry, my transition is messed up. Terminal velocity. Terminal velocity occurs when the gravitational force from Earth is balanced out by air resistance. When that's the case, the net force acting on an object is equal to 0. So when the gravitational force from Earth is balanced out by the air resistance force, we have a net force equal to 0. If something has a net force equal to 0, what happens? Or what doesn't happen, I guess. Go with that. Eris said the object doesn't move. How about the object doesn't accelerate, right? The object will fall with a constant velocity, right? Eris, does that make sense? Yeah. Right? It gets back, there's a question, I guarantee, hey, write this down and I'll tell you what the question's going to be, right? If the net force is equal to 0, an object has no acceleration. It will not change what it's doing. It will continue to fall, but it will fall at a constant velocity. Any good?
Does this happen for everything? Like if you let it fall for long enough?
Yes. So how much air resistance something feels depends on its shape, and it depends on its ratio of surface area to mass. Okay? For example, right? Let me see if I can do this. Probably not, but trying to make a little parachute out of this piece of paper. Okay. All right. So, first, which one has more mass?
Ball.
The ball, right? And therefore, what can we say about the gravity that's acting on the ball versus the paper? It's greater. But does that mean that the ball will accelerate faster than the paper? Not because of gravity, right? Gravity would accelerate them both at the same rate. But which one has a greater surface area? Paper has a much greater surface area, right? Meaning that it will run into much more air and experience a much greater air resistance, right? So, Andy, while this ball falls, it does experience air resistance. But because it's round and because it's smooth, right, it moves through the air pretty easily. It will increase air resistance the longer it falls. But in this room, it just doesn't really fall long enough to experience a lot of air resistance. But this, because it's so light and because it has such a big surface area, experiences air resistance almost immediately. And because the gravitational force on it isn't very big, almost immediately the air resistance balances out the gravitational force. And therefore, what will happen to the paper when the air resistance balances out the gravitational force?
It'll be in equilibrium.
It'll be in equilibrium. Will it still fall?
Yes.
But it will fall
Constant velocity.
at a constant velocity. Does that make sense? Okay. Let's see if this works. I doubt it. But okay. It flipped, right? But you can kind of see as it's falling, at least for the first part here, right? It hits terminal velocity. The paper hits terminal velocity almost immediately because it doesn't have very much gravity acting on it to begin with, and it experiences a lot of air resistance. So almost immediately it hits terminal velocity. But this one continues to accelerate because it doesn't experience as much air resistance. Yeah. Good there. All right. So, going back to our picture of Bronco. Does that mean now that that's it? Is picture C all that's going to happen to Bronco? What do we have to do in order to change what's going to happen to Bronco, Nick? And that's going to do what? Give more air resistance, right? We can't change the gravitational force. That's going to be the same because his mass never changes. But we can change the air resistance, right? Nick, what does the parachute do in order to increase the air resistance acting on Bronco? How does the parachute increase the air resistance on Bronco?
It has more surface
It has more surface area, right? If it has more surface area, what does it run into? It runs into more air resistance, right? So now, going to letter D, right? What's the net force acting on Bronco in letter D?
Minus 2 meters per second squared.
Let's go with the net force first.
Minus 200.
Minus 200 is the net force. Why, Andy? Why minus 200?
Because the resistance is higher than the weight.
The air resistance in the upward direction is higher than the weight in the downward direction, right? So it's negative 200. And then that means, Andy, that his acceleration is? Negative 2 meters per second squared. Okay? Eris, building on what we just talked about before, right? Now his acceleration is negative. What's going to happen in this case?
He's actually slowing down.
Now he's actually slowing down, right? He's still traveling in the downward or the positive direction, but he has a negative acceleration. And physically, that means that he's going to slow down, right? So now he's slowing down, right? Connor, are you good with the difference between, the acceleration decreasing, but it's still positive, but now it's negative, right? Yeah. All right, letter E. It's all going to stay, or yeah, it's all going to stay. Let's see if we can do this real quick. All right, so if we go down here to letter E, right? Acceleration at letter E should be negative 10 meters per second squared. right? But now he's slowing down. That being the case, Nick, building on something we said before, if he's still traveling downward, but he's slowing down, what's going to happen to his air resistance? It's going to decrease. He has a big surface area, which initially causes air resistance to increase. But now that he slows down, he experiences less air resistance. And eventually, he ends up with air resistance being 1,000 newtons again. What's the net force acting on him at letter F? 0. And therefore, his acceleration will be what? 0. Guess what we call that? Equilibrium. What else would we say? Terminal velocity. Is it the same terminal velocity as in letter C?
No, it's constant.
No. Terminal velocity in C would be constant as well. But is it the same velocity? No. Why not?
Because he has more surface area.
Different shape, right? Different shaped objects experience different terminal velocities. Okay? Terminal velocity is a general term when the force of gravity and the force of air resistance are balanced. But what terminal velocity is, or the actual value of terminal velocity, depends on the shape of the object, how big it is, what its surface area is, etc., etc., etc. Okay? Good there? All right. For homework tonight, part of your homework for tonight, we're not done with class yet, but part of your homework tonight, I would like you to answer these 8 questions that are over here on the side about Bronco's fall to the earth. I will post the answers online so you can check out those 8 questions. Okay? Good there. All right. What I would like you to do next, the sheet that I gave you today, it says Introduction to Friction. On the back of it is a picture that looks like this. Okay? Grab that sheet out, and let's discuss. All right, let's make this bigger so we can see it better. And I won't have to worry about erasing things. All right. So, all right. So it's a crate filled with delicious junk food. It's got to be delicious junk food. Okay, that's a lot of junk food, by the way. So, hey, awesome. Just want you to know, recording is going. So this will be recorded for all posterity. So. All right. So it says crate filled with delicious junk food rests on a horizontal floor. Only gravity and the support force of the floor act on it, as shown by the vectors W for weight and N for normal force. Okay? So, as this crate sits here motionless on the horizontal floor, what is the net force that's acting on it? Net force has to be what? Actually, let's do this. Why don't you guys do the first 4 questions, and then we'll talk about them together. So, do the first 4 questions. Talk to the person next to you if you need to, and we'll talk about them together as a group. Go. Let's take one more minute, and we'll come back together and discuss. One more minute.
Like
30 seconds.
G less than 0.
All right, let's discuss. So it says, crate filled with delicious junk food rests on a horizontal floor. Only gravity and the support force of the floor act on it, as shown in the vectors for W weight and normal force N. So, what I'm going to do here as I'm going through this, I'm going to highlight important information that you need to make your decision about answering these questions. What's the one word that is important in this little description of the situation that is going to help you make this decision? I would say there's one word. Rests, right? That's the important word in this part here, okay? That being the case, Mark, what has to be true about the net force? Has to be zero, right? Okay? The evidence being the highlighted word rest, right? Good there. All right, for number 2, it says, a slight pull, P, is exerted on the crate, but not enough to move it. A force of friction now acts. So, what is the important part of this sentence here, or this description?
Not enough to move it.
Not enough to move it, right? If it's not enough to move it, Mark, what does the net force on it still have to be? 0, right? That means, that actually answered the second question, right? And that means what has to be true about P and F? They have to be equal. Okay? Now, the next one is a little tricky, right? But let's just take it for how it's written. Okay? It says, a pull P is increased until the crate begins to move. It is pulled so that it moves with a constant velocity across the floor. Right? So, Lauren, just because we talked about it before, what's the important part of that description that we need to answer these questions? The constant velocity, right? Moves with a constant velocity. Okay? If it's moving with a constant velocity, we would say what about it? It's not accelerating, or it's in equilibrium. That being the case, right, if we go from the bottom up, the net force on the crate equal to 0, right? Constant velocity means the acceleration is 0. And that means that friction F has to be equal to P. As the description is written. Does that make sense? not the only one, just so you know. Okay? Here's the question, though. Okay, or here's the problem. Okay? This is showing the box as it's already moving. This isn't right when it starts to move. Could it start moving if all of these forces were equal? It couldn't start moving like that. But once it's already moving, if we balance the forces, right, what takes over? Inertia. If it's already moving and we don't have any other forces acting on it, what does inertia say it's going to do? Just keep moving, right? In the hallway, when we did the lab on Friday, the force I was exerting on the people skating down the hallway was not equal to friction. And as a result, what did those people do as they were moving down the hallway? They accelerated, right? They went faster and faster and faster and faster and faster. But if I started them moving and then I didn't pull quite as hard, right, just enough to balance friction, we would see that they wouldn't accelerate as we pulled them down the hallway. They would just go at a nice constant speed. But if it tells you it's moving with a constant velocity, all those things have to be equal. It can't start moving this way, but once it's already moving, that can be the case. Okay? And then for number 4, pull P is further increased and is now greater than friction F. Right? The important part here is what? Greater than friction. Right? That being the case, Eris, the net force on it is going to be greater than 0. And that means if the net force acts towards the right, the acceleration acts towards the right. So if we watched this box, Eris, what would we see about this box? It would accelerate. Specifically what? It would speed up. It would be going faster and faster and faster. Okay? Good there. All right. That's good for now. We'll pick up with friction tomorrow. I would like you to work on those 8 questions about terminal velocity. I'll post the answers online so we can understand that idea, and we'll pick it up with friction tomorrow. Okay?